Hello students, welcome to the 15th lecture on particle physics. And in the 14th lecture, we were discussing about parity. And what I had told you that the parity is an operation of spatial inversion, and it is not simply mirror reflection. Therefore, you can see this example. The above figure shows a mirror reflection of hand, while the below figure is representing mirror instead of mirror reflection, inversion. And therefore, the coordinates x, y, and z is changing to minus x, minus y, and minus z. And that is why yesterday when we were discussing it, I wrote when parity operator acts on r, it gives us minus r, resulting a change in the momentum, no change in the angular momentum, whether it is orbital or the total angular momentum, etc. We have seen the effect of parity on electric field, on magnetic field. We have seen that Maxwell's equations are invariant under parity operation. Then we also discussed about intrinsic parity and orbital parity of a system. We saw that we cannot determine the parity of leptons and baryons. Then we determined the parity of photon, parity of pi 0, and parity of charged pions. Now, just to recall that how we obtained the parity of charged pion, let me just repeat it. What we did, we took a pi minus beam on a deuteron target, and what I had told you that this is a slow absorption of pion on deuteron to have two neutrons in the final state. Now, pion is a spinless particle. Deuteron's spin is 1, while deuteron stays 96% of the time in S state, and therefore orbital angular momentum 0 state we took into account, and then the total angular momentum we found out that spin is 0, deuteron is a proton-neutron bound system which stays 96% of the time in S state, and then this pion absorption takes place in the atomic S state, and that corresponds to L equal to 0. Therefore, L equal to 0 and S is equal to 1 coming from the deuteron's spin results as the total spin of the initial angular momentum of the initial state equal to 1, and that is also the total spin of the initial state because angular momentum in the initial state is 0. Then in the final state we have two neutrons. These neutrons are spin half fermions, and therefore spin for both of the particles they are half, resulting as a total spin of 1 or total spin of 0. This total spin of 1 we saw yesterday that this results in a projection of +1, 0 and -1 state, while S is equal to 0 gives us Sz is equal to 0. Therefore, in principle, we have 1 + 1 state, 1 0 state, 1 -1 state, and 0 0 state. Then we saw that 1 + 1 state we can form when both the neutrons are in a spin up state. Then 1 0 we can form when one of the neutron is in a spin up state, the second is in a spin down state, and vice versa for the second case. And this 1 by root 2 is coming because of the Clebsch-Gordon coefficient, and then this is both of the neutrons are spin down states, and for 0 0 we had 1 by root 2 spin up for the first particle, spin down for the second neutron, minus spin down for the first neutron and spin up for the second neutron. And this minus sign is coming because of the Clebsch-Gordon coefficient, whose value is minus 1 by root 2 for the case where we have half half 0 minus half plus half 0. Therefore, for this case, since this Clebsch-Gordon is minus 1 by root 2, therefore this minus sign we are getting because of that. Now, when we all these four terms, we find that the first three, 1 plus 1, 1 0 and 1 minus states, they are symmetric states, and as we interchange the position of the two neutrons, there is no change of sign, while the fourth state, that is a 0 0 state, is an anti-symmetric state. Therefore, if we speak about the overall symmetry term that we will get from the spin factor, that is minus 1 to the power s plus 1. Therefore, if s is 1, like this here, we have a positive sign, while s is 0, we have a negative sign, and that will correspond to the anti-symmetric state. Therefore, overall symmetry from the two spins, we are getting a factor minus 1 to the power s plus 1. And then from the orbital part, we have another factor of minus 1 to the power L, as we had seen yesterday, that parity of pion times parity of deuteron minus 1 to the power L. This was equal to minus 1 to the power L parity of neutron times parity of neutron. And what we saw, that since the absorption is taking place in the pion absorption is taking place in the atomic s state, therefore this was L equal to 0. Deuteron's parity is positive. Therefore this factor is giving us plus 1. Therefore the parity of pion, on the right hand side we have these two neutrons parity, and we take the parity of neutron to be even, and since there are two neutrons, therefore it will always be positive, and the factor that we have is minus 1 to the power n. Therefore we have a factor of minus 1 to the power L, and with this minus 1 to the power s plus 1, an overall factor in the final state we have minus 1 to the power L plus s plus 1. Therefore, the final factor that we have on the right hand side is L minus 1 to the power L plus s plus 1. Since these two neutrons are fermions, these are described by anti-symmetric wave function. Therefore, this L plus s plus 1 should be odd. That would imply L plus s should be even. Therefore, the important catch is that my L plus s should be even and my Jf should be equal to 1. This is because the total angular momentum has to be conserved in any process. Therefore, Ji is 1. That is why Jf should be 1. Now we have to see that what would be the possible values of L, and that is why we talked about, since we have only two choices for S, either S equal to 0 or S is equal to 1, then we took the different possible values of L. L equal to 0, L is equal to 1, L is equal to 2, L equal to 3, L equal to 4 and so on. What we have to see, that L plus S should be even and Jf should be equal to 1. Now when we take S is equal to 0, L equal to 0, what you can see is that L is 0, S is 0 will give you, L is 0, S is 0 can only give you J is equal to 0. While L is 0, S is 1 will give you J is 1. But L plus S is not even, which is another requirement. Therefore, this is not possible, that L equal to 0 and S equal to L is L is 0, S is 0, or L is 0 and S is 1, these are not possible. Then we look for the other possibilities where we have L is 1, S is 0. Again, this will give us J is equal to 1. But again, L plus S is not even. Let us take another case. L is 1, S is 1. This will give us JF L minus S to L plus S. Recall the angular momentum algebra. The possible values will go from L minus S to L plus S in steps of unity. Therefore, the possible values of are 0, 1 and 2. Therefore, what we see that we have one Ji is equal to 1. We are getting Jf is equal to 1 with L plus S as even. That was the requirement. Therefore, it's fine. This is one of the choice that we have L equal to 1, S is equal to 1, resulting as Jf is equal to 1 and L plus S as even. Let us see the other choices. S is 0, L is 2. Now you see that L plus S is even, but Jf is 2, while we require Jf to be equal to 1. Therefore, this is not a choice. Let us take the other one. S is 1, L is 2. Now Jf will be from 2 minus 1 to 2 plus 1. That means 1, 2, 3. But L plus S is odd. Therefore, this is again not possible. Though we have Jf is equal to 1 here, but L plus S is odd. Therefore, this will not be possible. Therefore, S equal to 1, L equal to 2 is also not the choice. S equal to 0, L equal to 2 was also not the choice. Let us take any other example more than that. Say I am talking about S is 0 and L is 3. Then L plus S will not be even. And if I take S is equal to 1 and L is equal to 3 this time, then J will be, then notice that J cannot be then 1, then J will be 2, 3, 4, and therefore that is not equal to Ji, and therefore that is also not possible. Therefore, the only choice that is left is we have S is equal to 1 and L is equal to 1 to have L plus S even and Gf is equal to 1. And that is why we say that this value L is 1 and therefore the parity of charged pion is odd. Therefore, we have determined parity of neutral pion as well as the parity of charged pion in the last class. Now let us come to a very interesting result that was of early 1950s obtained from the accelerators. Two strange particles were observed. One was called tau, the other was called theta, and this is known as theta-tau puzzle. Why it was a puzzle? Because it was found that these two particles have the same mass, they have the same charge, they have the same lifetime, and they have the same angular momentum state or same spin. Okay, therefore these two particles were observed. These two particles had same mass, same lifetime, same charge, and same angular momentum. But what is the difference? The difference is that it was found that tau plus decays to 3 pions, pi plus and pi minus, and theta decays to 2 pions. Therefore, it was found that this tau plus is decaying into 3 pions and theta is decaying into 2 pions, while their masses, lifetimes, charge, and spin, they are all exactly the same. Now, if we want to determine the parity of tau plus or parity of theta plus, then we have to keep this in mind that again the total angular momentum of the initial state, this is Ji is 1, and we know that whatever pion we talk about, the spin of the pion is 0. Therefore, the total spin is 0. Here also the total spin is 0. But we have here 3 pions. Therefore, we will have a factor of minus 1 to the power L12, the relative orbital angular momentum of 1 and 2. And then when we have that system, then we have to consider the relative orbital angular momentum of the third pion with respect to 1 and 2. And then we have here 2 pions, and then we will have a factor of minus 1 L12, and this will be the factor times parity of pi plus times parity of pi 0, and here we will have a parity of pi plus times parity of pi plus times parity of pi 0. Therefore, parity of tau on will have, for the 3 pions, will have this factor, while parity of theta plus will have a factor of minus 1 to the power L12 p pi plus times p pi 0. And we have determined the parity of pions to be odd. Therefore, from here we will get a factor of minus 1. Therefore, this will give us minus times minus L12 plus L3. While here, since these two multiplication of minus 1 and minus 1 will give us plus 1, and therefore here we will get a factor of minus 1 to the power L12. Therefore, we have a factor of minus to the power L12 from here, and here we have a factor of minus outside, and then minus 1 to the power L12 plus L3. Now, since spin is 0 for the 3 pions or the 4 pions, and to conserve angular momenta, we have to see that this combining with spin, and spin is 0, that means this guy L12 plus L3, this should give us J equal to 1, and here L12 should be equal to this J. The catch is that if L12 plus L3 is 1, then this quantity is minus to the power minus 1 to the power 1, and that means this is positive, and this fellow is minus 1 to the power 1, and this will be negative. Therefore, parity of tau plus will be positive and parity of theta plus will be negative. Everything is fine. That parity for the first particle is positive, for the second particle is negative. That means one is decaying into parity even state and another is decaying into parity odd state, while having the same masses, same lifetime, same charges and same spins. Now, this is what I have written: parity for 2 pions, here parity for 3 pions, and where we have defined L12 and L13, and J theta plus I am telling you, since S pi net is 0 for the 2 pions as well as 3 pions. Therefore, what if we have J total angular momentum of the initial state is L12 for theta plus and L12 plus L123 for tau plus. Therefore, parity of theta plus is minus 1 to the power L12, and that is the same as minus 1 to the power J for theta plus angular momentum, and here this will be minus times minus 1 to the power, this quantity is J tau plus. From the above equation, it is clear that theta plus and tau plus cannot have the same parities. One is even and another is odd. However, if parity is assumed to be conserved, then theta plus and tau plus are two different particles. While all the properties were same, only the parity of these two particles were different, and that is why people called it as theta-tau puzzle. it was suggested that parity may not be conserved in weak interactions. In fact, Li and Yang theoretically studied many processes, strong electromagnetic as well as weak processes, to determine the parity of the systems, and they found out that parity is conserved in strong and electromagnetic interactions, while parity gets violated in the weak interactions. Now, on the suggestion of Li and Yang, that this is a decay for theta plus and tau plus, where parity gets violated. At one time, but the particle is decaying into even parity state, and another time this is decaying into odd parity state, and these are weak interaction processes. Therefore, in the weak interaction processes, parity is good quantum number. And that was a big result or big suggestion, because till that point everybody thought that laws of physics are ambidextrous, that if you have a physical process, then the mirror image of that process should also be a possible physical process. But here we are talking about the fact that parity gets violated in the case of weak interaction. And they, on their suggestion, Wu et al. Performed this celebrated experiment in 1957 on the beta decay of cobalt nucleus. They took 60 cobalt nucleus which had total angular momentum of 5 with parity positive, that was decaying into 60 nickel, first in the state 4 plus, and then after emission of 2 gamma rays, this nickel was coming to ground state 0 plus. Therefore, what was the important point? That Wu et al. Took cobalt nucleus which had total angular momentum of 5 with parity positive, was decaying into a daughter nucleus, nickel star, which was in excited state, having in the state 4 plus, the angular momentum is 4 and parity is positive. And we know that the angular momentum should be conserved. Therefore, the angular momentum of the initial state must be equal to the angular momentum of the final state. Therefore, what they did, they placed this cobalt nucleus in a magnetic field and cooled this fellow to avoid any thermal vibration. Therefore, they had this cobalt nucleus in a magnetic field such that the spin of the nucleus, they align in the same direction. To polarize the nuclear spin, they put a magnetic field, and to keep the thermal vibration at the lowest level, they cooled it. Therefore, there was a magnetic field as well as there was a cooling. So, therefore, the aim of the experiment was to observe some spatial asymmetry in the emission of beta decay electrons from 60 cobalt, which could lead to a distinction between beta decay and its mirror image process. That means whether the number of electrons going in the northern hemisphere is the same as the number of electrons in the southern hemisphere or not. That means whether there is a preferentiality of the emission of the electrons in one direction or not. If there is a preference, then that means there is an asymmetry, and if there is an asymmetry, that means the nature is favoring a definite direction rather both the directions. Therefore, this is what was the aim of this experiment. Therefore, what they did, they kept this cobalt nucleus in a magnetic field at very low temperature to minimize thermal vibrations, and presence of the magnetic field resulted in the alignment of the direction of the spin of the cobalt nuclei along the direction of the magnetic field. Now, if in the real world everything is fine, then the electron should be emitted in all the directions, in same number of electrons in the northern hemisphere as well as in the southern hemisphere. And now if you look at the mirror image of this, then also, since we know that when we talk about parity operation, we have seen that J does not change under parity operation. And we have also seen in the class that magnetic field does not change under parity operation. Therefore, what changes? R to minus R, linear momentum changes P to minus P. Therefore, there will be change in the direction of the momentum of the particle. Now, the point is that they kept the magnetic field in one direction and then reversed the direction of the magnetic field. Now, when you will say that when the magnetic field is in the clockwise direction, then all spins are aligned in one direction. Now, say in the upward direction, in the clockwise case for all the cobalt, nickel and the daughter products. But when you reverse the direction of the magnetic field, then spin will be aligned in the opposite direction. When you are doing it in a magnetic field in the anti-clockwise direction, the spin angular momentum will reverse its direction and the alignment will be in the opposite direction, and such that again all these spins angular momenta will be in the same direction to give us J is equal to 5. Therefore, the important point is that first they thought that if nature obeys mirror symmetry, then in both the northern hemisphere and the southern hemisphere, we should get equal number of electrons. While when the experiment was performed, they found that the electrons prefer a particular direction. And there are only a few electrons in the opposite direction. The electrons are preferring a particular direction. That means more electrons in the southern hemisphere than in the northern hemisphere, opposite to the direction of the spin of the nuclei and the electrons, etc. Therefore, what they found that these electrons are in the one preferred direction, and that is, say, I am calling it as the southern hemisphere. Or when this is happening, that electrons are preferring a direction, and still if we reverse the magnetic field and now electrons are coming in the opposite direction. For example, initially when the magnetic field was in the clockwise direction and most of the electrons were coming in the southern hemisphere, now you reverse the direction of the magnetic field, and then that means your B has changed, the direction of J has changed. Or equivalently, you can say that I have got a mirror image where J and B have not changed, but what has changed? That my P has become minus P. Therefore, equivalently, either you say that the magnetic field is in the anti-clockwise direction and that resulted in the alignment of the spin in the opposite direction, or you say that what I am doing, in fact, for the parity, I am taking P2 minus P, my J and magnetic field, they are unchanged. Therefore, that means if the electrons initially were coming in one direction, when we take the mirror image, this time also we are finding out that now the electrons have preferred the direction in the northern hemisphere rather than in the southern hemisphere. And that means there is an asymmetry, there is a preference in a particular direction, and which proved that parity is not conserved in beta decay. This was a marvelous result where I have shown that total angular momentum is 5 and here it is 4 for the nickel, and these two particles, electrons and antineutrinos, their spins are aligned in the same direction, as you can see, to give you the total angular momentum of 5. And we have discussed earlier that under parity operation, n angular momenta, they are not going to change. Therefore, the important point is Magnetic field is not changing. The angular momentum of the system is not changing. What is happening that when we are talking about the emission of electrons in to be symmetric in nature, it was found that not at all it is symmetric. It prefers one direction, and that means there is an asymmetry. When we have taking the magnetic field in the clockwise direction, it is preferring southern hemisphere, and when we are taking anti-clockwise direction, then it is preferring northern hemisphere. And that means the electrons are not coming out in both the hemispheres in equal numbers, and that tells us that nature is preferring a particular direction of the electrons, and that is what we say that parity is not conserved in weak interactions. Thank you very much. Let us stop here.